I'm Ante Q, and my work is on computer methods for collision processing from sound to topology. Physics simulations of objects in contact help emulate the world in many application areas, including animation, augmented reality, and fabrication. Examples include layers of chainmail stacking on top of each other, a shopping cart rolling away, and a scarf falling onto an incline. The first half of my thesis covers the synthesis of ground sound from object-ground collisions. Many sounds occur when objects are in contact. When objects collide, their surfaces vibrate. These vibrations drive sound waves through the air. Prior works physically model the vibration of these objects, but not the ground. My work models the ground using a regularized geophysics solution. Here's an example where 13 steel ball bearings are dropped onto a wooden floor and sound is synthesized using a finite difference time domain wave solver. Here's the ball sound. Now here's the floor sound. Now here's the combined sound. In this scenario, the combined sound is different from the ball sound alone, which is missing the floor. My thesis explores the scenario parameters that affect the ground sound significance. The second half of my thesis verifies the topology of loopy structures, such as chainmail and yarn-level cloth, as they undergo collisions. Here's a simulation of a chainmail pile. Each sheet consists of interlinked rings. Unfortunately, in this case, a ring falls off and rolls away, because the collision is missed between rings. This error is hard to catch visually. I propose fast linking numbers, a topology certificate for loopy structures. Given a model state, my method computes a linking number certificate before and after processing to enable automatic topology verification. Here's a chainmail simulation we computed. There aren't obvious visual errors here, but is it correct? My method says no, there are broken links. In the prior work, a simulator was used to prepare chainmail for 3D printing by packing it into a box. My method catches topology errors before printing it out. Let's also look at yarn-level cloth modeling. This sweater model was relaxed using a yarn-level simulator. How do we know whether the relaxation avoided pull-throughs and maintained the yarn topology? Here's a yarn-level cloth simulation where we take a sweater and drop it onto the ground. We can mark topology violations in red. Here's a rerun with smaller time steps. Both simulations took many hours to complete, but only a fraction of a second to verify each visual frame.
Hello, I'm Hui Ye, a PhD student from City University of Hong Kong. My research during the PhD lies on the intersection between computer graphics and human-computer interaction. I have been exploring novel mobile AR prototyping tools for 3D contents and interactions. Augmented reality benefits various applications, but existing tools for 3D contents creation are not easy to author in situ 3D contents in AR, especially in close interactions with physical environments. So, the main goal of my research is to fill in this gap by exploring easy-to-use and intuitive interactive techniques for in-situ 3D content creation with mobile AR. We first studied the fundamental issues of using an AR-enabled mobile phone as a 3D pen. By eliciting studies for natural phone grips and input points, we present a mobile AR interface for 3D curve creation and refinement. Users can easily create 3D curves closely interacting with physical objects using a mobile phone, and interactively refine the curves to their desired shape. We also show the applications of this interface to direct 3D drawing on and around physical objects and using a mobile phone as a direct length measurement tool. Following this line, we further explore in-situ 3D character animation in mobile AR. Existing approaches for AR animation usually lack close interactions with physical environments. We've approached this issue by exploring to use a mobile phone to directly represent and control AR animated characters. We first conduct illustration studies to understand what motions are commonly needed and what motion gestures naturally correspond to such motions. Then design and develop AR Animator, a novel mobile AR system for authoring 3D character animations in close interaction with physical environments. Users can easily create 3D character animations using the motion gestures of a mobile phone and interactively edit the animation results. In-situ 3D content creation with mobile AR is an emerging topic. I'd like that my research benefits the whole research community and brings diverse applications for industry. Thank you.
Fluids are almost everywhere. My thesis focuses on developing computational imaging methods for the reconstruction of fluid flows and underwater geometry. In the first project, I proposed a novel fluid measurement system, which is termed as rainbow particle imaging velocimetry. This is an overview of the system design. The depths of the particles are color-encoded by a rainbow light. A specifically designed optics is mounted on the camera for all in-focus imaging. Using the rainbow PIV system, the fluid flows are reconstructed by tracking the motion of the particles. To achieve this, I perform a novel joint optimization for the estimation of sequential particle distributions and velocity fields, which are physically constrained by the fluid properties. Here is a video about injecting water from the bottom. The left is the captured video, and the right is the resimulation of the particle motions and path line visualization from the recovered time-varying fluid flows. This video refers to dripping a drop of water from the top. The recovered flow fields in both cases are consistent with the observations. In the second project, I proposed the first single-camera solution for underwater geometry reconstruction in the wild. This is a video captured by a camera placed above the water surface. Our main observation is that the distortions from the moving water surface provide a changing parallax for each point on the underwater surface. This information can be utilized to triangulate the underwater geometry. The inputs to our model are a sequence of frames captured by a single fixed camera. We then compute the dense correspondence from each frame to a reference frame. We fit the flow fields together with initialized water surface and scene geometry into a novel differentiable framework, where the water surface and the scene geometry can be simultaneously optimized by minimizing the framework loss. It finally yields quality reconstructions on the 3D structure of time-varying water surfaces and underwater geometry. Here are two videos taken in a public fountain with different wave strengths. The recovered water surface agree with the observed distortion patterns. In both conditions, the overall underwater environments are well-surfacely recovered. Here are two more data captured in a seawater environment. The proposed method still realizes a robust recovery in these challenging situations. In conclusion, my work enables the volumetric flows and underwater geometry to be recovered using simplified setups.
My thesis aims to automate the robot design process with computational methods. As a robot is a combination of its hardware and software, robot design involves non-trivial optimization over its body and brain. As of today, robot design is still extremely labor-intensive and error-prone. Consider the task of designing an aerial robot. As shown by these three examples, the design space is very diverse, highly unstructured, and therefore requires engineers to explore manually based on their past experience. My thesis aims to automate this design process with computational tools and covers multiple essential aspects of a robot design pipeline, which combines shape and controller design, physics simulation, optimization, and real-world evaluations. Specifically, my thesis makes 3 unique contributions. Firstly, we develop a computational pipeline for co-designing the shape and controller of a real-world aerial robot. Our pipeline covers design, simulation, optimization, and fabrication of an aerial robot. Our method allows amateur users to discover novel robot designs that outperform an expert design from engineers by a large margin. Secondly, we develop advanced differentiable simulators for inverse design problems in soft and underwater robots. Developing differentiable simulation methods for such systems is typically challenging due to their high degrees of freedom. Unlike existing differentiable simulators, we provide numerical methods and insights in gradient derivation, allowing us to expedite gradient computation greatly. Lastly, we provide a technical solution to the sim-to-real transfer problem, which is very common after computationally designing a robot in a virtual environment. Our solution leverages the differentiable simulator we developed to narrow the sim-to-real gap, allowing us to directly transfer a trained controller in simulation to this soft underwater starfish in a real-world experiment. We observed that optimization using our differentiable simulation leads to similar dynamics motions in simulation and real-world experiment. This concludes my presentation. Thank you for watching.
When light shoots on a surface, it bounces into the surface and bounces out somewhere else and creates a soft look, and this effect is subsurface scattering. We like the effect from light candle, fruit, and jade. But what we care most in real-time rendering is photorealistic digital human. Subsurface scattering is hugely important for scheme in game and virtual production because getting it wrong can lead to horrible results in the deep of the uncanny valley. The state-of-the-art real-time subsurface scattering uses Birdie's subsurface profile to perform Monte Carlo sampling, but the GPUs hit large sample counts and incoherent memory access due to Monte Carlo sampling. To spend like 80 milliseconds for real-time subsurface scattering in games? No way. Then I started exploring real-time rendering techniques to deal with this issue, which later becomes a new taxonomy. In the taxonomy, homogeneous real-time rendering techniques try to reduce coins, samples, and memory access uniformly, while heterogeneous techniques try to reduce them non-uniformly. A major heterogeneous real-time rendering technique contribution in this dissertation is real-time adaptive sampling. Our real-time adaptive sampling technique is constructed on the fundamental relationship between sample count and variance in Monte Carlo sampling. We have a novel single-pass sample count estimation method to use in-frame history to predict the sample count in the current frame, and replace the oldest frame sample count with a prediction using temporal projection. The grayscale in the bottom image visualizes the predicted sample count at a certain frame. Normally, it would take ON for both space and time. However, adding the technique itself overruns the benefit. Instead, we propose an O1 approximation which makes adaptive sampling efficient for real-time applications. Our algorithm has good performance for stable sims. However, dynamic lighting leads to unstable performance due to temporal variance overestimation, resulting in sample count overestimation. To remove the temporal variance overestimation, we can apply a general spatial countervariance. Countervariance reduces variance by approximating the integrand with a simple function that can be integrated analytically and using Monte Carlo to adjust compute the residual between them. To remove temporal variance, we find temporal countervariance more appropriate. With countervariance, we have a more stable performance. This enables better performance in themes like disocclusions, gunshot, lightning. All of them are pervasive in games. Thanks. Please read my dissertation for more details.
Sketching provides an intuitive intermediate to depict design ideas. Image-to-image translation provides a general solution for sketch-based image synthesis tasks. This thesis explores the topic of sketch-based image synthesis in three aspects: corrective control, imperfect input, and generation quality. In Sketch 2 Normal, we propose an interactive system to convert the hand-drawn sketches to normal maps. We enhance the corrective control by incorporating the user-specific point hints. Our system achieves superior normal map generation quality with great ease. And here we show the shading effects of two generated normal maps. We feed the sketch image as the input of the generator, and then feed the intermediate normal map together with the sketch as the input of discriminator against the ground truth. Here we show examples of interactive control sessions. And here we show an interactive drawing session of the result. In deep face drawing, we resolve the imperfect sketch input with a retrieval and interpolation mechanism. Our system boosts the performance of handling imperfect input and achieves remarkable generation quality. We decompose a face sketch into 5 components. For each face component type, we learn a local feature embedding. We designed the feature mapping module with 5 separate decoding models converting feature vectors to spatial feature maps. The resulting feature maps are placed back to the original positions of the face. Given the combined feature maps, the image synthesis module converts them to a realistic face image. Given a new feature vector, we project its component to corresponding manifold. The found component images are then blended as shadow and placed at the corresponding component's positions for sketching guidance. Here we show an interactive drawing session using our system. And here are more results. To further improve the face generation quality, we utilize Style GAN in our drawing instyles. Our method modifies the unconditional Style GAN to a sketch-based image translation framework and enables flexible yet precise control for portrait image generation. To assist users in producing precise spatial conditions, we propose a suggestive drawing interface. Our SC Style GAN consists of a spatial encoding module and a subsequent pre-trained Style GAN synthesis module. Our network takes as input a sketch and a semantic map with the paired high-level style features and a randomly selected low-level style features in generation. Here we show an interactive drawing session using our system. And here are more results. In summary, we propose 3 interactive frameworks to convert sketches to high-quality images. We adopt various mechanisms to ensure the user control in the generation process.
We study the problem of inverse rendering at 3 different levels of abstraction. At the low level, we explicitly solve for every term in the rendering equation. These are physically based methods that estimate shape, reflectance, and illumination from appearance. At the middle level, we abstract away the intermediate light bounces and model the final appearance with the light transport function. We can also do relighting and view synthesis without actually solving for every term in the rendering equation. Finally, at the high level, we learn a direct mapping from appearance to the underlying shape or lighting, without even modeling the light transfer function. These are data-driven approaches powered by deep learning. In this fast forward, we discuss only these 3 projects. At a low level of abstraction, neural radiance factorization, or NeurFactor, is a physically based model that jointly solves for shape, reflectance, and lighting. We can do free viewpoint relighting with NeurFactor. Because NeurFactor models visibility, it can synthesize hard shadows. Note how the normals are smooth and yet detailed, and how the albedo is shadow and shading free. Because we explicitly model albedo and BRDFs, we can edit the material and then relight the edited scene. We can apply NUR factor to a mobile phone capture, since NUR factor handles a single unknown lighting condition by relying on priors. At a middle level, Near Light Transport, or NLT, models appearance with the light transport function, instead of factorizing the function into reflectance and lighting. We can just interpolate the light transport function to perform simultaneous relighting and view synthesis. We can also relight a person with arbitrary light probes. At the high level of abstraction, generalizable reconstruction, or genre, treats the image formation process as a black box to invert. Genre generalizes to novel shape classes unseen during training. Here are genre's reconstruction of the training classes, which contains detailed shape features. Here are the results on novel shape classes unseen during training, which also possess the detailed 3D structures visible in the input views. The work presented here would not have been possible without these amazing collaborators. Thanks for watching.